Most role-based access control systems turn into technical debt way faster than founders or developers ever realize. And why? Well, because the whole concept of role-based access just sounds so incredibly simple on day one. When you're launching a brand new SaaS product, you usually start with three basic roles, right? Admin, member, and viewer. It's clean, it's totally manageable, you just toss the user into one of those buckets and everything's peachy, until someone asks for a custom permission on a random Friday afternoon. That day one simplicity, yeah, it's completely deceptive. It is literally setting a trap for you. Because, well, reality happens. As your product grows, those enterprise edge cases start rolling in. And suddenly, your nice, simple three-tier system morphs into this chaotic, unmaintainable mess. I mean, think about it. You've got an admin super, an admin billing, a limited admin, a team editor. The list just goes on and on. Permissions start getting duplicated all over your codebase, the guardrails become practically impossible to maintain, and when you're dealing with roles like this, just one badly coded condition can instantly become a massive security vulnerability.
Welcome to The Explainer. Today, we are going to dismantle this broken system and look at a fundamentally better way to build your architecture. Our mission here is to figure out exactly how to transform that brittle, decentralized, and honestly messy role-based access control into a robust, centralized permission infrastructure, one that can actually scale with your business without introducing fatal vulnerabilities.
Okay, let's dive right in. Here's our technical blueprint for today. We'll cover the RBAC scaling trap, designing scoped permissions, server-side validation rules, the fail-closed principle, and finally, Redis caching at scale. All right, starting off with part one, the RBAC scaling trap.
This trap is almost always triggered by a completely reasonable customer request. They'll ask something like, hey, can our finance team export invoices but absolutely not manage the billing settings? Or maybe, can project managers invite users but only inside their specific workspace? You've definitely heard these before. These highly specific requests are exactly what forced developers to start hard-coding exceptions, duplicating logic across random utility functions, and inadvertently triggering major security drift.
So the ultimate solution to that whole mess is a centralized permission engine. The absolute golden rule of your architecture has to be this: authorization logic exists in one place. That's it. When you scatter that logic across different controllers and start duplicating front-end checks, it inevitably drifts. And as we all know, in software architecture, drift equals vulnerabilities. But by routing absolutely everything through a single core infrastructure system, you prevent that fatal security drift entirely.
Moving right along to Section 2, Designing Scoped Permissions.
We really have to stop thinking of roles as permissions. Roles are not permissions, guys. They're just containers. True authority comes from atomic, explicitly scoped checks. Relying on a broad check, like just asking if someone's admin status is true, is an absolute disaster at scale. Instead, the system should check something atomic, like if the user can export invoices for a specific workspace ID. This is a huge paradigm shift. You're checking an explicit action directly tied to a specific context, rather than just blindly trusting a generic title. But here's the thing. An atomic permission like invoice export or billing manage is completely meaningless without boundaries. Not all permissions apply globally, right? You need scopes to make that access precise. Every single permission must be scope aware. Like, does this apply at the global scope, the tenant scope, or is it restricted to just a single workspace, or even a specific resource scope? Scopes are exactly what ensure that an editor in workspace A doesn't somehow accidentally get editor rights in workspace B.
Which brings us to Section 3, Server-Side Validation Rules.
Now, the crucial point here is this absolutely non-negotiable rule. Front-end permissions are UX hints. They are not security. Hiding buttons or graying out menu items is purely for a smooth user experience. It does absolutely nothing to stop a direct API attack. An attacker can literally just open up their terminal, bypass your beautiful UI entirely, and hit your endpoints directly. So, permission evaluation must happen server-side only. Every single protected endpoint on your backend needs to enforce a strict 4-step validation lifecycle. Step 1, identity. The backend validates who is actually making the request. Step 2, tenant. It checks if this user actually belongs to the organization in the first place. Step 3, permissions. Do they have the specific atomic permission required within the correct scope? And finally, step 4, resource. Are they actually allowed to manipulate this specific piece of data? Only when all 4 of these checks pass with flying colors is access granted.
Next up, Section 4, the fail-closed principle.
I want you to think about this for a second. What actually happens in your system when permission resolution fails? Like, what does your backend do if it cannot definitively prove a user has access? Do you let them through just in case, or do you block them? This is arguably the most uncompromising security stance you have to take in backend design. Now, what's really interesting about this principle is how incredibly strict it is. If permission resolution fails for any reason, we're talking a network timeout, a database hiccup, whatever, the result must be unequivocally strict. Access denied. Boom. The request is logged, an anomaly trace is captured for the security team. You must never, ever put your authorization check in a try-catch block and just casually return true on the catch. Permissive failures are a massive vulnerability. Security systems must fail closed, deny by default, and only allow when explicitly authorized, no exceptions.
And finally, Section 5, Redis caching at scale. Because here is the painful truth. Permission systems become expensive really fast. If you follow the strict rules we just laid out, you are running complex, multi-layered queries, checking identity, tenant, scope, and resource on literally every single backend request. Doing that directly against your primary database? Yeah, that's going to bottleneck your entire system. It's simply unsustainable at scale. So let's talk about caching and see how this builds a real solution to that exact bottleneck. To keep things blazing fast, we rely on specific Redis caching strategies. First up, we use Redis permission snapshots. Instead of hammering the database every single time, we store a snapshot of the user's evaluated permissions right in Redis, giving us incredibly fast authorization. But wait, what if an admin revokes access? Well, that's where version-based invalidation comes in. The exact moment a membership changes, that cache window is evicted in Redis. This guarantees real-time revocation. So you get the ultra-low latency of a cache paired with the strict real-time security of a live database. It's truly the best of both worlds. So, as we wrap up this explainer, I want to leave you with a provocative question to help evaluate your own systems. Most startups think RBAC just means tossing in some roles and calling it a day. But as we've seen, real production systems need scopes, policies, resource ownership, revocation strategies, and completely centralized evaluation. Looking at your own codebase today, ask yourself, are you building a demo architecture, or are you building a truly scalable SaaS platform? The choice of how you handle permissions right now will absolutely dictate whether your system scales securely or collapses under its own technical debt. Thanks for joining me for this explainer, and we will see you next time.